Okay, good morning, everyone. So welcome to the Sharjah Academy for Astronomy, Space Science and Technology. So we welcome our SAASST research assistant and also our student from University of Sharjah and also from our guests from outside the University of Sharjah. So this workshop is part of our activities in terms of enhancing our knowledge from our point of view, from the technological point of view, from the scientific point of view. And CubeSats, as you may know, does link all of this all together. So I would like to have this workshop to give more information about how we can achieve science with less and less and less and less funds. So this is very important for us because we as a university, so we can't afford to build large systems. That's why it's good to go through small systems. I believe this is what every university worldwide is doing. So achieving science with CubeSat, this is a very, very nice title. And as we move on from slide to slide, hopefully you get more and more information about it. So let me show you the content of this workshop. First of all, I will give like a prelude or short introduction about CubeSats, the different types of CubeSats and so on, and what is going on right now, so up to this past August. Then Mr. Mohammed Rayhan from the Radio Astronomy Lab is going to give his shot about having low-cost proposals, low-cost systems. Ms. Tarifa Al-Ka'bi and Mr. Yusuf Farouk from the CubeSat Lab are going to talk about the heart of this workshop, about CubeSats and how they can be used and so on. And Dr. Antonios, along with Noor Al-Amiri and Mariam Al-Qasimi from the High Energy Astrophysics Lab, are going also to talk about how we can use CubeSat to do real science, especially in the X-ray domain. And as you may know, the Sharjah Academy for Astronomy, Space Sciences and Technology is willing to launch, hopefully by next year, June 2022, its first CubeSat to be a 3U CubeSat. If you don't know what is 3U, hopefully you get to know more about it. So to be dedicated to study the sun in X-rays and also to be able to observe some other stars. So this will be like, so this workshop will give you hopefully more insight about CubeSat and science and so on. So let me start with my first slide, just an introduction to give more information. So you may ask yourself, how heavy is a satellite? Well, this is a very nice slide that or picture that I found through the Canadian Space Agency, so just for you to feel how big and how small. So what we are talking about in this workshop. So if we take a large satellite, so it can be an internet satellite, it can be a weather satellite, it can be any of the telecommunication satellite. You may be talking about something more than 1,000 kilograms. So these are big systems. A medium satellite, we go less than that. And you can see here on this pulsar, so they were showing several animals, a rhino, and so on. If I take a mini satellite, it may be between 100 to 350 kilograms. If I take a micro satellite, you can see the kilogram like a wolf. And if I take a nano satellite, 1 to 10 kilograms here, we are talking about CubeSats. You see how small it is. If you compare a large satellite, more than 1,000 kilograms, it may cost hundreds of millions of dollars. And you take a nano satellite, that may cost maybe a couple of hundreds of thousands of dollars. That's why they are very affordable. That's why so many universities since 1998 are building and are sending these beautiful small satellites. So this is how it is. So this is just to put you into perspective. So what we'll be talking in this workshop is about nano satellites, something that is small, that we can afford more or less to build and also to operate. So A CubeSat, usually we use the letter U, CubeSat. So it is a very, very small miniaturized satellite for space research. It can be from the technological point of view, it can be from the scientific point of view. So you have different payloads. Usually the 1U this is the size 10 by 10 by 10 centimeters. So the mass for this 1U is no more than 1.3 kilograms, and usually they use very simple elements. We call them the commercial off-the-shelf components. We call COTS. So and most of these components are space hardened, so they can sustain space environment and so on for a short period of time, for sure. And you can put your CubeSat. Usually when you have a big satellite, we need to have a rocket, and that rocket also may cost tens of millions of dollars. CubeSats, on the other hand, you can use the space station, the International Space Station. They are this kind of deployers where you put your system inside and to be launched from the ISS, or you may use a big rocket. Sometimes in these big rockets, they have some empty space around, and you can use them to have like a secondary payload, and the cost will be much, much less. Usually a single rocket, after for sure using its primary payload, it may also carry more than 100 CubeSat, and this happened so many times in the past. So up to this past August, more than 1,600 CubeSat have been launched into space. Okay, and this is quite astonishing, because this is quite a big number. So let me show you this nice histogram showing the nanosat, which is here we're talking about CubeSat and so on launches from 1998. Look at it, 1998, only two, as you can see to the far left of this histogram, and as you can see, the number has been increasing since then. So 2000. Let's say 19, about 188. What you are seeing in red is just the launch failures. Either the satellite or the rocket failed, or maybe the deployer did not open and the CubeSat wasn't launched. So we have so many types of failure. But as you can see, so the failure is very small. It's very small. So it is risky, but it is very small. So the chance of sending your CubeSat is very high. So as you can see, the number is increasing. We're expecting that by 2025, also more than 700 CubeSat will be also launched by 2022, as you can see, and hopefully our Sharjah CubeSat will be launched by 2022. This is just the distribution by countries. If we can just look at the Middle East, as the Middle East, so Saudi Arabia 1, the United Arab Emirates 5, so you have several countries in there, and as you can see, the largest number of CubeSat have been launched by the United States of America. So many, but as you can see, so everyone would like to send these beautiful babies to do something, to test technology, or to do a scientific experiment. This is the same thing. So the distribution by continent. Look at it here: the US more than 1,700, Canada, Europe, South America, Africa 29.20, about 0.9%. Nothing, but at least there is something going on. So everyone is working very, very hard. This is histogram showing the different types of CubeSats, the different sizes. So you can go up to about 16 EU CubeSat, and you can go much smaller than that. So, but as you can see, so the average CubeSat is a 3U CubeSat, which we have 1U plus 1U plus 1U all together. So most of the CubeSat are in the 3U range. You go higher to 6U, to 8, to 12U, it will become more and more complicated, and you need a lot of technical resources to do that. This is just to show the nanosatellite orbits, how high they go. So usually we say LEO, low Earth orbit. So you can see here. less than 400 kilometers, between 400 to 550, and above 550. And for sure, the higher you go, the longer the lifetime of your system will be. So less than 400, so you're going to get a lot of drag. That's why most of these CubeSats will not survive a year. We are for Sharjah Sat 1, so we're expecting it to live at least 2 to 3 years. So we have, at least we have 2 or 3 years, hopefully, of good data. So this very nice histogram showing you the orbit of most of these nano satellites. In terms of who is sending them, so you can see on this histogram, mostly by companies, private companies, the highest number about 1,700. The universities, well, because CubeSat is part of space education, but even a primary school in US was able to send one CubeSat in 2016. And space agencies, military applications, non-profit institute and schools. So at least, and even you have individuals, so private persons sending their own CubeSat and so on, if they have the means and also if they have the knowledge. So most of these satellites, so most of these small satellites that have been sent by companies, even though they have the means to send big ones, but most of these CubeSat will be sent to test some technology. In terms of scientific applications, so just to name a few, we have so many applications. If we take our electromagnetic spectrum, so people have been sending these CubeSat to do some optical, some infrared observation, some X-ray observation, some gamma ray observation. If you'd like to do GIS remote sensing, so you can do that using this, what you call the hyperspectral imager, and also using spectrometers. So as you can see, we have so many applications of this CubeSat, and the trend is going on, so it won't stop at just this specific field. So it will go to cover so many different applications, because they are affordable. You would like to check something for a couple of months. You would like to test something in space. So the best way to do it now at a very low cost is to have a nano satellite being built by your company, by university, or by any other entity. So this is very promising in terms of this is scientific application and also engineering application at the same time. So this is quite affordable. So this is what we can use as a CubeSat. So let me now move to the next speaker. So our research assistant Mohammed Rayhan from the Radio Astronomy Lab. So he is going to present his part. It will be the low-cost space research importance and challenges. So please, Mohammed, take the stage, and whenever you would like to change the slide, let me know, and I will move forward. Okay.
Okay, thank you very much, Professor Elias, for this introduction. Please let me show you, or to start the presentation.
I'm not hearing you, Mohammed.
Sorry, can you hear me? Can you hear me? It's okay? Yes. Okay. Let me start with the low-cost space
problem
research. There is a problem, Professor? Can you change the slide, please?
So just give me 1 minute to fix it up, inshallah.
Yes.
Okay, do you hear me now, Mohammed?
Yes. Yes, Professor, I can hear you. What about you?
Do you hear me, Mohammed?
Yes, yes, Professor. Yes, I can hear you.
Okay.
I don't know if the other audience can hear us. Yes.
Yes, they can hear us.
I
Yes.
had feedback from some of them. Yes.
So they're hearing you.
Yeah.
Okay. Okay, let me go. Let me know when I need to go to the next slide. Okay, I am ready.
Yes.
Sorry for
please.
this small technical problem. Sorry.
Yes, thank you, Professor. Let's go to the outline. Now, let's discuss this 4 points. The first one, why we should reduce the cost of the space research. The second one, the budget, how to make a budget radio astronomy projects or radio telescopes. And I will make a very, very short comparison between the low-cost radio telescopes and the CubeSat industry. And finally, I will talk about the SAASST experience as one of our projects. Next slide, please, Professor. Yes. Now let's see what the previous projects were cost in the past, and how many how the cost now, how much it costs now in our prices and the current prices. So we know the economical problems and the inflation and what else. All prices is going to increase. So that's why for the first one on the left array, this is a Mills cross array. This array that used to discover the first planetary radio observations in the 50s by Franklin and Bork. So they did and built a very, very large array to detect faint signals from Jupiter. But now we can, with a very cheap or not very cheap, it is cheaper and simpler or more simple equipment, we can build an array to do the same function for this long array and high cost array like this one. Also, the interplanetary radio telescope that used by Jocelyn, you know, the astronomer lady Jocelyn. She the first person who discovered the radio emission from the pulsars. This is also a very large array, and it needs a large amount of antennas and large area and so on. And the old guy, the radio telescope in Jordan Bank in UK. So this radio telescope also could be replaced by a smaller telescopes with less cost and expenses. Why we get this? For me, in my perspective, there are 2 factors that steer the space or radio astronomy research toward the low cost radio telescopes. The first one is technology. So instead of building a huge dish like this one, you can, by using a small dishes and make an interferometer to do the same results. Also, the same with the Mills cross array. Our current equipment are more advanced, more sophisticated. The computer, the AI also help us to reduce the cost of these equipments, these old equipments. And also, it is important to encourage new researchers to enter this industry, this field, this space research. It is important to do projects with less cost. If you start doing your projects in very high cost expenses, it is not good to enter this field for students, for colleges, institutes, and so on. So this is very important to start with a low cost radio astronomy. Next slide, please. Here is an example for some ambitious projects. Actually, there are a lot of new projects based on computer softwares and use a very simple antenna, very simple and affordable equipment and tools. These projects depends on the more technology, depends on the advanced electronic devices, like what we will talk in later, inshallah. So some of these projects had done here in SAASST. So we did one of this. This one, the top right picture, we did the same array first as a prototype radio telescope 3 years ago, and after that we expand this radio telescope as we will see in the SAASST experience. Next slide, please. Yes, this is the first project. It is a radio Jovi project. Also, this project is an educational and public outreach program that involving scientists and teachers from NASA and other organizations to start or to trigger the idea of the doing research in radio astronomy with this low-cost tools like what we see. So you can collect all of these tools in one table. So this is very very good for students to do or to start the radio astronomy research. And the same thing did with the other projects by some of them by NASA and some of them by the other international research centers like Jet Propulsion Center, as we see in the next slide. So the next slide, it is about the yes, this is the Super SDI monitor. As you see, there is no antenna. This system uses no antenna. It depends on the VLF instead of HF radio astronomy. So it is one of the projects that receive the effect of the radio solar radio storms. After the radio storm, there is a what we call the sudden ionospheric disturbance. So after that, you can find this negative effect of these storms. So it has not received the radio storm, the radio emission from the sun, directly from the sun, but it can detect its effect. So it is very simple. Needs a piece of the antenna itself. It is a small coil, and you can put it indoor instead of put it outdoor. It doesn't need the mast or support system or structure. So this is one of the ambitious projects. Please, next slide. Yes, this one. It is a radio array for abortable interferometric detectors. So this is very important. This is driven by GPL, the Jet Propulsion Laboratory. I think it is in MIT. So as you see, this unit is working or take the power from the small solar panels like this, and it is a portable one. So it is very small, it is very compact, and if you build many of these low-cost antennas or antenna unit, you can and use the technology. The main idea is using technology, using the advanced softwares to decrease or to reduce the expenses by using this new technology and low cost equipment. You can get a good results. You can get advanced results actually. Next slide, please. Yes, here is examples for the antenna that are commonly used in the low-cost radio astronomy. We use a simple half-wave dipole. I will not describe all of them, and we may use an inverted V dipole and the folded half-wave dipole. And this dipole, as you see, it needs only tubes, metal tubes, or carbon fiber tubes, and wires, and needs something is very important. It needs a good knowledge in electronics and computer science and everything to reduce the cost and to get better results. The next slide, please. Yes, about the receivers, no need or instead of invest in large receivers for like what they did for the previous arrays, as we see in the beginning of this presentation. You can see this one. It is a very small. It is a mobile phone. The larger one is a mobile size kit like this one, used as a receiver for a very wide range of frequencies. And you can see also use a smaller one. It is a USB size. It's called SDR. So the SDRs now and the softwares, most of them are free, by the way. These softwares designed for this SDRs, and they are designed for observing the sky in multi-band width. Next slide, please. Yes, in case if you would like to expand, don't use one single antenna. You can do this array. You can build this array, combine more than one antenna with each other, and call this array as a unit. If you'd like to expand more and to do interferometry, you can build multiple units of these, like what we have in what they have, sorry, in LOFAR radio project in Europe. So they use very simple dipoles like this one, inverted V dipoles, and put it in groups, and these groups combine to each other, and by using the interferometry, they connected with the other bus in other countries. So this is a very large aperture radio telescope with less cost. It costs too much for sure, because it is spread around the whole Europe. I think about all countries in Europe, I think, or more than 10 countries are a part of this large project. But as one unit, it is not too much expensive project. Next slide, please. Yes, what we have in SAASST. In SAASST, we get the idea of the simple radio telescope from the Jovi radio telescope project that we discussed before, and expand this system. And we have two arrays, each array connected with a separate receiver like this, and each receiver connected with its computer, and we can control and receive and recording these data remotely from our labs. The operating frequency is at 20.1 megahertz. and this system is designed to absorb the solar activity, radioactivity, and Jovian radio storm also. So this is inside the cabin. The cabin, it is outdoor. This building, it is on the SAASST equipment area near to the main building. Next slide, please. Yes, this is a virtual visit for this area. This is a 2 array, and you can see here the single array. It is used to observe the solar radioactivity during the summer, and the dual array it used to observe Jupiter and also the solar radioactivity. The cabin is here at the middle. Inside the cabin, you saw the computers and receivers and all facilities inside. The conclusion is, yes, before the conclusion, just let's make a short comparison between the low-cost radio astronomy and low-cost satellite technology and space technology. So the CubeSat and nanosatellite, it is a solution for many financial problems and financial challenges, because you can build a small satellite or nanosatellites or CubeSats like this one, and instead of build a very large one and invest in millions or hundreds of millions to build one, you can build a cluster of these, and you can collaborate with other cluster systems, and you can build your cluster to observe, for example, to observe the water distribution on Earth, on the Earth, the planet Earth, and you can contribute with the other entities and other universities and research centers to do the same thing and to collaborate with their data. Next slide. So the CubeSat, it is. I will not discuss it because we have experts in CubeSat now. They will describe this more in details. But it is as a principle, it is simple. So this is a conclusion: is the strongest radio sources. We can do research with strongest radio sources with very low cost equipment, and we can do it as an entry for students in all stages to do and to encourage them to enter this field and do research furthermore in radio astronomy and also in space and any space research. Thank you for this for listening, and hopefully if you have any question, I think we will keep it at the end of the presentation, Professor.
Yes, we keep the question at the end. Thank you very much, Rayhan. So just to inform everyone who is attending that a window will pop up in about noon time for you to write your email to get your certificate, and for my student to get bonus points. So let's now go to the next presenter. So it is two research assistants from the CubeSat lab. So let me start first with, I believe, Yusuf. So Yusuf, please take the stage.
Hello, good afternoon, everyone. It's still morning. All right, so I will be talking about a CubeSat. What is a CubeSat in general? I believe my colleagues have discussed it earlier, so I will just breeze through it. So a CubeSat is a satellite that has a specific form factor. It consists of units. Each unit is 10 by 10 by 10 centimeter, and it should have a rough estimate mass of 1 kilogram per unit. And what's nice about that is that you can scale it. So you can have 1 unit, 2 units, 3 units, 6 units, 12 units, and you can just fit them all together and make a relatively large system. Can you go next? So why do we build the CubeSats? That's a really interesting question. First of all, it's accessible to everyone. You can be a high school student. Some high school students in countries like Japan, the United States have already built their own CubeSats. Universities are currently building the CubeSat. As Professor Ilyas mentioned earlier, we are building our own, the first CubeSat out of the University of Sharjah. So it's accessible to everyone. You don't have to go to specific contractors or specific engineering firms. They are relatively easy to build, and it is affordable. So a 1 unit, an average price of 1 unit could go between 100,000 US dollars. If you go towards the conventional large satellites, the cost can reach up to millions of dollars. Given that it is small and it is really relatively scalable, it is easy to develop. So I can have it designed. I can buy some components off the shelf. I don't need to make. I don't need to make any components in my laboratory. So I just buy everything and stick it together. And it's flexible engineering. So let's say I put a 1080p camera today, and the technology is not available for a higher quality image in the next year. Let's say a new camera comes out and it's a really good camera. I do not have to go back to the design board and waste 2 or 3 years of design experience. I'm just going to stick the new camera in. It's very modular, and this gives it an advantage. I can design it, build it, and launch it in less than a year if I have all of the components available. Next. All right, so how do we use CubeSats? One of the, not primarily, one of the best things that we can do is understand Earth. And we can do that in a mission that's called Earth Observation Missions. You can see in the picture, there is a CubeSat. It's about 2 to 3 U in size. The company is called Planetary Sciences. They have this CubeSat. As you can see, it is, I put a mug to scale. It's around the same size. My coffee mug is a little bit big, but that's like a, yeah, you can say it's about 2 mugs in size, 2 mugs in coffee size. And most of the images in my presentation are going to be from what this satellite has taken. So what is Earth observation? Earth observation is gathering information about, the planet Earth, its physical properties, chemical properties, biological systems, agricultures, and I think I put a timer on my slide again, So we can go to the next slide. So why is Earth observation important? Earth observation is important because it can help us forecast the weather. We're getting a lot of data at each time the satellite passes. I can have 1 satellite, 2 satellites, as many as I want. They're small, they're cheap, they're affordable, easy to launch. So I can have a constant stream of data to monitor the weather, wildlife, forestation, deforestation, desertification. Is the Amazon shrinking or is it growing larger? Who knows? If I have an image every hour or 2, I can easily tell. I can respond to natural disasters faster. If I have forest fires, if I have floods, tsunamis, I don't need to go to a big satellite company, wait until their satellite passes, and then it's going to take that image and send it down to me. So we can see a volcanic eruption here. This has been taken by the Dove-2 CubeSat, which I included the picture of it earlier. Next. So what about agriculture? Yes, if you have a camera that's pointing down, it's always good, right? Like they always say, look at the bigger picture. And with CubeSats, we can look at the bigger picture easily. So when you're looking at agriculture, sometimes it is hard to notice patterns at a macro scale. If you're a farmer that you have to go through and walk each and every field, especially in larger scale agriculture, that's not going to be beneficial to you if you can tell if your crops are doing good or bad, and you have to monitor each tree. However, if you have a satellite or a CubeSat in general that takes an image of your crops, you can easily tell which crops are performing well, which are not performing well. As you can see in the time-lapse image, this is not an image from a CubeSat. I believe this is the only image that I have that's not taken from a CubeSat. This is from the East Owenat farms in Egypt, and we can see the growing trends in agriculture. Next slide. All right, economics. What does space systems or satellites have to do with economics? Well, the topic of today's talk is how does CubeSat help in sciences? And being an engineer in the industry, I know that economics plays a major role in our engineering decisions, in our life. It is a science after all. It's a social science that deals with the production, consumption, and the transfer of wealth between businesses. So what does CubeSats have to do with businesses? I'm going to give you an exercise after that. I'm going to pick a random name, and so stay watchful. So many of you want to know, are the oil prices going to go up or are they going to go down? Is this factory producing cars, or is the power plant producing enough electricity? We can tell from the images. If the factory is blowing steam, we can tell that it's working. If the factory has no, all right, yeah, if the factory has no, if the factory has no steam, no cars, no employees showing up, we can tell that this is a bad factory and we should not invest in it. Next slide. So this is a prelude to my exercise that I'm going to give. So we can see in the top left photo an oil tanker. So some satellites, these pictures are all taken by Dove satellites, by the way, the same 2 mug-sized satellite. So we can look at oil tankers every day. You know, it's like, is the tanker full? Is it half full? And then with our engineering estimates, we can tell how much does this country produce oil. Let's say, you know, they go on media and then they say we produce 1,000 barrels a day. Is that true or not? You know, if we have access to satellite technology, we can tell, is the oil price going to go up? Is the country producing oil, or are they not producing enough oil? And the prices are going to go up. So I should maybe gas up my car this month. Let's go to the next picture. So this is an exercise. I looked at the list of names and I see Mohammed Al-Khazindar. Yes, Mohammed Al-Khazindar. What do you think? Can you share your opinion? What do you think? Is the oil prices going to go up next month, or are they going to stay the same, or maybe less? I don't know if they can.
So I can see 3 huge tanks, and based on the photo you showed us previously, it looks like 3 of the tanks are nearly full, and the others are just half empty. So they have a pretty good oil supply. So I don't think they'll be buying from elsewhere. So maybe the oil prices over here will go up.
All right, so I'm going to fill my car like today, but then if the price goes low, I believe that we have the mailing list of everyone, whoever participated. I'll go after you and I'll make you pay the difference. so now you know the importance. Oh, and by the way, this picture, can you see the quality, the resolution, the shadow? This has been taken with a CubeSat. Isn't that amazing? You know, back in the day, people imagined those spy satellites are big, huge, and chunky, and you know, you need a lot of money to produce data and science. That's relatively true and not sometimes. So I'll leave the floor to my colleague Tarifa, and she's going to tell you a little bit more about CubeSats. Thank you.
Thank you very much, Youssef. So let's go to Tarifa right away. Please, Tarifa, take the stage.
Okay, thank you, Youssef. So another science that we can use CubeSats for is planetary science, which is a scientific study of planets, including Earth, moons, and planetary systems and the from them. So with this science, with this study, we aim to understand the solar system origins. So the objects in the solar system, how they form and evolve. We aim to search for the requirements for life in other planets by exploring and finding where life exists and could exist today, and to reveal planetary processes through time. And to achieve this, we require close proximity observations using sophisticated instruments for elemental and mineralogy measurements. And some observations may only be done with in situ investigations and sampling. So next slide, please. So if we wanted to use CubeSats for such a mission, there are some challenges that we might face. We know that the Earth has this magnetosphere that shields Earth orbiting satellites from the radiation that could impact and damage the electronics. So satellites that would travel to outer planets would need to have high radiation or radiation-hardened systems and shielding. Another challenge is the limited power. So beyond the orbit of Mars, light from the sun becomes very weak. So this would mean that we would need larger solar panels to continue harvesting energy to operate our systems. We also have limitations on the instrument volume and mass imposed by the CubeSat standard. We have limitations on the data retrieval because an interplanetary CubeSat would have to be able to communicate over tens to hundreds of millions of kilometers away. So larger antennas are needed to support this communication. And lastly, because of the long distance that the CubeSat travels to reach its target, we would need an efficient long-range propulsion systems that fits within the CubeSat form factor and enough fuel to take it through its long ride. So next slide, please. One successful mission is the Marco A and Marco B CubeSats, which are twin communication relay 6U CubeSats by NASA that were built to support the InSight mission. The InSight is a robotic lander on Mars that would be used to study the planet Mars. So these two CubeSats were used as a real-time communication link to Earth for InSight during its entry, descent, and landing when it was not in line of sight with Earth. And also, these were the first CubeSat missions to go beyond the Earth orbit, and they were used to test the new miniaturized communication and navigation technologies that would be useful for future missions as well. And with these missions, we are understanding if CubeSats can endure the deep space conditions that satellites that go to these orbits have to endure. So next, please. You can see here the subsystems of these CubeSats and an illustration of how they work. You can see the UHF antennas that would be used to receive telemetry data from the lander. And the high gain reflective antenna would be used to transmit these data to Earth with expand frequencies. You can also see the 8 cold gas thrusters that we need to steer the CubeSat towards Mars and also to do any course corrections in the way. And the large solar panels, of course, that we need to generate enough power to operate all the subsystems. Next, please. So as for future CubeSat missions to planetary science, we have the Artemis 1 program that is planned to launch in February of next year. And it will launch 13 6U CubeSats as secondary payloads. 2 of the interesting ones are the Near-Earth Asteroid Scout, with the main mission to fly by and collect data from a near-Earth asteroid. And as you can see, it will use a special solar sail for propulsion. And another CubeSat mission planned to launch with the same launching vehicle is the Lunar Ice Cube that will be searching for water ice and other resources from above the surface of the moon during its 6-month mission. And it will use a special instrument that will help NASA scientists to understand where the water on Mars is and its origins and how we can use it, which is useful for future lunar missions. And in the future, we expect to see more deep space planetary science CubeSat missions as these small satellites prove to be capable to perform beyond the Earth orbit. Thank you.
Thank you very much, Tarifa, for this nice presentation along with Yusuf. So this is part of the CubeSat lab. This is what these 2 researchers are doing, and hopefully they will succeed in launching our Sharjah Sat 1 by next year. So we go to the other team. So Dr. Antonios, Miss Noura, and Miss Miriam. So please take stage.
Assalamu alaikum, everyone. My name is Noura Al-Amiri. I'm research assistant at the High Energy Astrophysics Lab at SAASST. Now I will be giving you this presentation that will be about scientific contribution of CubeSat in the high energy astrophysics. Specifically, it will be in the X-ray astronomy. So can you go to the next slide? For this presentation, I will be following this outline. I will start with defining what is X-ray astronomy and what is X-rays and what type of X-ray we have, soft and hard, and what is the X-ray telescopes and X-ray detectors, and then we'll move to see how we analyze X-ray data, and then we'll see the different or several X-ray sources that will be presented. At the end, we will present like CubeSats that serve in the high energy astrophysics field. Next slide, please. So X-ray astronomy, by definition, is high energy astronomy, and X-ray astronomy is a branch of astronomy which deals with the study of X-rays, observations, and detection from the astronomical objects. And it's called high energy astronomy because probing X-ray emissions from several astronomical sources, like probing high energy processes occurring within the system. So in here we have an example of the Crab Nebula that has been probed using different wave band. We have radio wave, infrared, visible light, and ultraviolet and X-ray. As you can see, like using different bands, we can see different regions in the source. And using X-ray, we can see the most inner part of the source that give us the more information about the source itself. Next slide. So X-rays in general, if I wanted to define it, it's an electromagnetic radiation that ranges between 0.1 and 100 keV, and it has two types, soft X-rays and hard X-rays. Soft X-rays ranges between 0.1 to 10 keV, and they call it soft because it has high penetration in the water. And hard X-ray ranges between 10 to 100 kilo electron volt, and it has a very high penetration. And as you can see in this image, there is several applications of using hard X-rays. We use it in the airport security and medical CT and mammography and X-ray crystallography. So this is in general about the soft and hard X-rays applications. Next slide. So X-ray astronomy by default is a space astronomy because like most instruments to detect X-rays must be taken to high altitude using balloons, sounding rockets, and satellites, as you may know, because of Earth's atmosphere that has absorbed the X-rays and we can't receive it on Earth. In the image in here, as you can see, it's opaqueness versus wavelength. You can see in the X-ray ranges, we have opaqueness reaches 100%, which means that we can't receive X-ray on Earth. That's why we have to have our telescopes on the space. Next slide. So X-ray telescopes are not like optical telescopes. X-ray telescopes are telescopes that is designed to observe remote objects in the X-ray band. And the basic elements in the X-ray telescopes are the collimators and the detectors. Collimators are to collect the radiation, and the detectors are to collect and measure the radiation coming from the source. And we have a variety of different designs and technologies have been used in order to develop these instruments. So in here we have two examples of X-ray telescopes. We have grazing incidence and the coded mask. Grazing incidence telescope, or so-called also water telescope, is a telescope for X-rays that only uses grazing incidence optics, which means that mirrors that reflects X-rays in a very small angles or shallow angles. And coded masks are grids. Coded masks are grids or gratings or other patterns of material opaque to various wavelengths that can detect electromagnetic radiation. Next slide. So I'll leave now the floor for my colleague Mariam in order to continue the presentation.
Thank you, Laura. Hello, everyone. My name is Mariam. I'm a research assistant at the High Energy Astrophysics Lab here at SAASST. So, as Laura said, that X-ray telescopes detect X-rays, but how they detect it? They do that using X-ray detectors. So, X-ray astronomy detectors are instruments to detect X-rays to study X-ray astronomy, as the name indicates. So, X-ray astronomy detectors usually interested in detecting energies, but sometimes do detect wavelengths, and that depends on the technologies of construction of such detectors at the time. So most existing X-ray detectors uses what we call is CCD, or a charge-coupled device. A charge-coupled devices that what is a charge-coupled device? It consists of capacitors that can convert energy photons detected into charges and then read out as images. Most digital cameras use CCDs, and most detectors use CCDs. So after detecting the X-ray using detectors, we analyze the data. Can you go to the next slide, please? So our X-ray data is interesting. It's different than the optical astronomy data, where its primary data set is an image. While for an radiant interferometry, the primary data set is a visibility array. But for X-ray astronomy, the primary data set is an event list. So an event list consists of an array of four-dimensional array of the position, X, Y, and time and energy. In this data, most of the pixels are empty. So every photon is really precious, and we're really interested in every photon detected. So the data received, we can obtain an image, as you can see through the top right of the page of the slide. Here you can see an image of an X-ray binary system. Below it, you can see a light curve. That light curve usually gives us the intensity of the source. And finally, at the bottom right, it gives us the spectrum that tells us some physics of the source. Next slide. So to obtain this data, we obtain it from different sources. So what are the sources that emit X-rays? We call it astrophysical X-ray sources, which are astrophysical sources that emit X-rays. We need to read these X-rays to understand them and get the data that I just showed that we need to analyze. So there are several types of astrophysical objects that emit X-rays. Most known are the galaxy clusters. Quasars and black holes and active galactic nuclei also emit X-rays. Galactic objects such as supernova and remnant stars and binary stars, X-ray binaries. X-ray binaries are an interest of our lab, and finally some solar system bodies. Next slide. As I said, X-ray binaries is an interest of our lab. So what are they? They are a class of binary systems that are luminescent X-rays. They consist usually of a compact object and a donor star. The compact object pulls matter from the donor star, creating an accretion disk. This accretion disk is created when gravitational potential energy is given, and when that is given, we have an emission of X-rays. This emission of X-ray that we are interested in analyzing and obtaining different physical properties of the source. Next slide, please. So how is that related to our workshop, CubeSats? So CubeSat are we have many famous CubeSat that study, that gives insight into high energy astrophysics. One famous one is the CubeSat. This is developed by the Australian Space Agency. Its mission is to detect gamma ray bursts and electromagnetic counterparts of gravitational wave mergers. Also, we have a IXS CubeSat. This is a CubeSat developed by the Southwest Research Institute, and it was chosen by NASA to continue the study of it. It's a CubeSat imaging X-ray solar spectrometer. It measures the elemental composition of hot multi-millionth degree plasma in the sun's corona. And finally, we have the Black Cat CubeSat. This CubeSat is developed by the Penn State University and the Los Alamos National Laboratory. As you can see that most of them can be developed by universities, so it's easy to develop by students like you guys. So what's a Black Cat CubeSat is a soft X-ray sky monitor. It's transit finder and the burst detector for high energy multi-messenger astrophysics. And finally, we have our own, next slide, our own Sharjah CubeSat. Its main payload is an X-ray detector, or what is called an improved X-ray detector, IXRD. The mission of our Sharjah Sat-1 is to cover bright hot X-ray sources, especially for black hole transit. Example, a source called Vela X1, which is a high mass X-ray binary hosting a neutron star, and many others. And also to catch gamma ray bursts and giant soft gamma ray bursts. So this is the main objective, scientific motivation of Sharjah Sat-1. And that's it for us today. Thank you. You can skip that. Yeah.
Okay.
Okay.
Thank you very much, Noura, and also Mariam, for this presentation regarding the use of X-ray in terms of observing this very hot region, especially this neutron star, X-ray binaries, and so on and so on. I believe now you can see on your chat, you can see the link for those people who would like to get the certificate, and also for my students. So please click on the link and write your name, your student ID. The link will expire in about 15 minutes. So let me now open the floor. If you have any questions, I'm checking the the chat. If you have any questions, so please you can ask right now. Please, if you have any questions.
Assalamu alaikum.
Wa alaikum assalam wa barakatuh.
To be honest, I don't trust my headphones now. I hope you can hear me well.
Yes, I do.
Do you? Okay, thank you very much. I would like to thank all colleagues at SAASST for this excellent workshop. Thank you, Professor Ilyas, as well, for the organizing. I have a question which is always comes up to my mind when we say a CubeSat, and because of the fact that CubeSats are very limited in size, you know, it is 10 by 10 roughly. So, you know, we know when it comes to optics and when it comes to observation, even cameras with lens, actually they use the principle of telescopes. So when we need more details, which is the resolution in technical terms, that means the bigger is better, you know. When you talk about small f or focal ratio, that does not give good pictures or high resolution. Also the focal length, so both they give better resolution and also power magnification. When we have that very limited size, so my question, what is the limitation of the observation, especially when we want to observe things on the Earth at height at least 150 kilometers? I think maybe that's the lowest CubeSat can be. You can tell me better. So this is even a huge distance at limited size of focal length and limited size of focal ratio, the diameter of the lens. So what is the limit of having good pictures, high resolution and high and good power magnification? Anyone can answer.
Yeah. Thank you, Marwan, for the question. Well, as you said, it all depends upon your application. So we said earlier, my colleagues said it, that it is a low-cost system. So for sure, we'd like to have high resolution, better coverage. For sure, bigger is better, as we said in astronomy. But for university people, so especially researchers that have very limited funds, so these small systems are very useful. Yes, they are limited. You cannot do everything, but you can do a lot of research. You can initiate, because most of these cubes, especially those that have been sent by universities, it is for space education. It's to educate the student, the space engineering student, in terms of building the system. In terms of resolution, let me give an example. Our Sharjah Sat-1, that we fly about 550 kilometers above Earth's surface, will have
the altitude again.
550 kilometers.
Okay.
This is the low Earth orbit.
Low, of course.
So our Sharjah Sat-1 is equipped with two VJ cameras, and Yusuf can correct me. It has a resolution of about 40 meters. So when it does fly above Sharjah city, it can take a very nice picture of the Sharjah Academy. So it all depends upon the usage. So what you would like to use it for. So for GS remote sensing, to observe, and also for X-ray detectors. So it will be able to observe the sun, the coronal holes, meaning it will be able to observe this very hot region, the corona, and it will also be able to observe, as Miriam said it, this bright X-ray star. So it all depends upon the usage. So the application is unlimited. It's unlimited. But the main focus that people are using them is for space education. So to educate people, the students, and as we mentioned so many times, they are affordable. The average price about $100,000 if you don't count for sure the launch cost.
Yeah.
If Yusuf would like to add something, please add it, Yusuf.
Yes, generally speaking, your constraint is on the lens, not on the sensor of the camera. So
actually both.
Yeah, both. There is a limitation on the lens, there is a limitation on the sensor, but usually I think when you're talking about the zoom, it's optics. So if we can go back to my slides, these are images that has been taken with a 2-unit CubeSat. If you look at the CubeSat is nothing but just a lens and a sensor and a little bit of subsystems. So when it comes to limitations, really your imaginations can go wild. It all depends on your mission. And as Dr. Ilyas said, one of our cameras, I'm not going to go a lot into the technical specifications, but one of our cameras is a 5-megapixel camera with a resolution of 50 meters. So we can, with 50 meters, we can take a really good image of SAASST. And to a level of extent, we can tell how many cars we have in our parking lot.
At what resolution you can, at what megapixel you can get the car size, which is 5 meters pixel, I believe.
So we have 50 meters. So with 50 meters, you can get a really good image of SAASST.
But not car size or
you can tell if there is. You can't tell if it's an individual car, but you can tell if there is car parked. That's how much I can tell. But you can do better. Like this image has been taken with a Jovi satellite. You can pretty much
maybe 1
see,
meter, 2 meters, I believe. This one, it's very.
This is about 25, I believe. This is about 25. I'm not sure.
No, 20.
You can go back
the
to
pixel means 1 pixel, which you cannot distinguish. This is 25. I believe this tank is about maybe 50 meters in diameter, but you can see it very, very clear, which means it's maybe 2 meters resolution. This is what I believe. I'm not sure, but beautiful picture. But anyway, so there's a limitation.
This is taken with, if you go back to the picture of the satellite, just maybe 2 slides back, Professor. Back. Yeah, that's like, as you can see, it is nothing but a telescope with a sensor in the back.
Exactly.
If you'd like to go to 1 meter to half a meter, you have to go to Khalifa Sat or Dubai Sat 1, Dubai Sat 2. This is very big systems. But CubeSats do not have that capability unless technology is going to advance so much that we can have small sensors that can have such a resolution. Yes.
Yeah.
Any other question from the attendee, please?
Professor, can you hear me?
Yes, go ahead, please.
Me and someone else, we could not use our university email, so we used our normal email. Is that fine? I sent you an email as well.
That's fine. As long as you write your name.
Yeah, no problem.
Yeah. Any other question, please, from the group? You can chat, you can write it. You can write your question. Okay, so there are no questions. I would like to thank all of the research assistants who presented their talks today. So it is an extra work for them. So I appreciate their help in keeping us always busy in these presentations, and also to highlight what we are doing at the Sharjah Academy for Astronomy, Space and Technology. Just to add something, that our Sharjah Sat-1 is our first experience for the University of Sharjah. We have several systems on our drawers. Hopefully, we get enough fund to build these systems. As we said and as we stress, this is for space education, and hopefully everyone at the University of Sharjah, especially those engineering students, science students, are going to benefit from the systems, because we do conduct a lot of workshops related to satellites, CubeSat, and so on. And by the way, just to inform everyone, this coming Thursday, we're going to have a very specific workshop related to STK. STK is one application that we use to simulate CubeSat launches, CubeSat operation, and so on. So anyone is welcome, but this workshop will be an on-site workshop, and the number of places is very limited. So we accept only about 20 students. That's why we're going to announce it, and if you're interested, you are welcome to attend on-site. It will be from this coming Thursday, November 25, from 11 to 1 o'clock. So from 11 to 1 o'clock, it will be on-site at the Sharjah Academy for Astronomy, Space and Technology. It will be in our smart room. So if you are interested, if you are an engineering student, science student, would like to at least touch how do we simulate a CubeSat or any satellite, so please, you are welcome. So once you see the ad, so please, you have to email us to be able to register you. So again, thank you. I would like to thank all the participants and also those people who attended this workshop, and hopefully they were able to get an insight about CubeSats and also their scientific use. They are very affordable now for every university to build its own CubeSat. So if there are no further questions, so I would like to end this workshops. Thank you again. And for those people who would like to get a certificate, so please send us your reply before 2 minutes from now. So because the link will close at 12:15. Thank you very much, and assalamu alaikum.
Assalamu alaikum. Thank you.
Thank you.
شكرا جميعا. بارك الله فيكم.